All right, so let's do this. Let me share my screen. I have not. I'm going to grade it this evening. Yeah. Right. So if you can recall, the 4 steps of hypothesis testing, okay, that was on the exam. So 4 steps of hypothesis testing. First step is state your hypothesis. I'm going to take you through an example and the way how it's all written down and worked out. Okay. Okay. Set the criteria for a decision. Okay, so our alpha level, our significance level, 5%, either 1% or 0.1%. Okay, we're going to talk about that. Select your data. So in our examples, you won't have to collect the data. The data will already be collected, but you will have to compute your sample statistics. So you'll have to compute your Z-score, you have to compute your T-score, whatever that is, but you'll have to compute that. And then the last thing is you're going to use step 2, the criteria that you set. You're going to use step 2 in order to make your decision in step 4. Okay, so whatever you use for step 2 will be used once you get your statistic. You'll compare your statistic to whatever the criteria is, and then you'll make your decision either to accept the or reject the null hypothesis or to fail to reject the null hypothesis. Okay, so I'm going to go and move into an example. But first, I wanted you to look at the criteria. Okay, so in step 2, it's required that you set a criteria or a critical region. And so when you set your critical region, you can set it at 5%, which is here. Your critical region is that extreme 5%. So this is 95%. These are high probability values. And then the extreme values are in the shaded. Okay? So if your statistic falls in this region, you're going to fail to reject the null hypothesis. That means it's not. These are if your statistic falls out into this region, is typically different, right? So it means 1.96, negative 1.96, those are Z-scores for a 5% significance level. Okay. If we go, I think I showed you. Okay. I'm gonna take it. So for a 1% significance level, so on 2.33. Yeah. 2.33. And then the 0.01% is like 3.3. No, I'll take the last one. Trying to see if I can find it. But I think those are the only 2. Yeah, 3.30. Right. So 5% significance level. The Z-score for that is plus or minus 1.96 or 1% significance level. Z-score is plus or minus 2.58. Yep. 0.01%. 0 plus or minus maybe 3 point. Okay. So these scores are the critical region, right? They identify the critical regions in a graph just like that or a distribution just like that. So at levels, okay. So you'll have negative 0.96 here, negative 2.58, negative 3.30 there. And you'll have 2.6, 2.58, and 3.30. Okay. As you decrease your significance level, you also decrease your critical region, right? So that means the scores for the critical region becomes a lot more extreme as you decrease your significance levels. Okay. So it makes it a lot harder when you find a significant difference if you were to decrease those values. Okay. Right. Let's move. All right, we did that one. We're good on that. We did this. We're good on it. Right. I think we just did this one. So the true false said that the alpha level is decreased. The size of the critical region also decreases. Right. So again, these are your critical region alpha levels as you decrease them. The critical region also, it goes from 1.96, that's 5%, 1%, and then 0.01%. So they also decrease, right? So that size of that critical region will also decrease as well. Okay? It says the critical region defines unlikely values if the null hypothesis is true. We said this is very, very true, right? So if the null hypothesis is true, then these values out here, they're very, very unlikely. Okay. And so that's what that second bullet means. Okay. The critical region defines unlikely values. These are the unlikely, rare, extreme values when the null hypothesis is true. Okay. All right. I think we're good. Step 3. We went through that. This is the statistic that we've learned, the Z-score. I'm going to take you through an example and it'll make more sense. We don't need that. We did all that. Good. Good. I think this is, yeah. Okay. All right. So 8-2, uncertainty and errors in hypothesis testing. So like we talked about before, when you are solving a hypothesis test, always subject because a hypothesis is an educated guess or prediction, right? So if it's a prediction, that means that I don't know it 100%. I'm predicting, right? So when you think about hypothesis testing, it is an inferential process, meaning I'm trying to draw a conclusion based on information that's not complete information, but I'm using a sample that is not complete to then draw conclusions about a population of people or a population of whatever it is, right? So it's using a limited amount of information. It's not everything from a sample to make a statistical decision, which then is used to make a conclusion about the population. Okay. The sample data is then going to make the statistical decision. It allows us to make an inference to then draw that conclusion to the population, right? So once we do those 4 steps, when we make that decision at step 4, we're then going to be able to either draw a conclusion about the population or not be able to draw the conclusion about the population based on the data that I collected. Okay. Errors, it says the last one, it says errors are possible because it's almost impossible that you're going to be able to collect data on the entire population, right? And so since you're not able to collect data on everyone in the population, there's going to leave some room for error because I can't get everybody in the population, right? So my sample is always going to be slightly different than the population mean or standard deviation, simply because I can't get all the information that I need for the sample. Okay. And the error that we talk about is called the sampling error. Okay. It's called the sampling error. All right. Good. Got it. So there are two types of errors that you can make when making the decision. When you're doing your making your statistical decisions, right? The first error that you can make is what we call a type 1 error, okay? The type 1 error, it indicates that the researcher rejects the null hypothesis when the null hypothesis is actually true, okay? So that means you reject the null hypothesis, your value may fall into this area, but there's no difference at all, right? So we're making an error in that we're saying that there is a difference when there is actually no difference whatsoever, okay? So the research is concluding that the treatment has an effect when there is no change, no effect whatsoever, right? That's a type 1 error, okay? The alpha level is the probability that a test will lead to a type 1 error, right? So if you set your significance level, your alpha level at 5%, it's saying that you have a 5% chance of getting a type 1 error. Okay. If you set it at 1%, that means you have a 1% chance of getting a type 1 error, meaning rejecting the null hypothesis when the null hypothesis is actually true. Okay. So again, type 1 error determines your probability of obtaining a sample in this critical region, right? Even though the null hypothesis is actually true. That is a type 1 error. You want to know the difference between type 1, and then I'll show you the next one for type 2. Okay. Any questions about type 1 error? So when you reject the null hypothesis, we're saying that the values that we get for our sample statistic, is falling into these critical regions. Right? When we make a decision to reject the null hypothesis because it falls in this critical region, we reject the null hypothesis, right? We're saying that when you set your significance level, your alpha level, reject the null hypothesis when the null hypothesis is true is a type 1 error, right? So when you create your critical region is telling me how much likelihood it is that I'm going to get a type 1 error. Because again, the type 1 error is rejecting the null hypothesis when it's true. Okay. So again, when I have it at 5%, I have a 5% chance of getting a type 1 error. When I set it at 1%, there's a 1% chance I'm getting a type 1 error. So on and so forth. Okay. Great question. Any other questions about type 1 error? Okay. Type 2 error. Okay. Type 2 error says that you are failing to reject the null hypothesis when the null hypothesis is actually false. Meaning, I don't find a significant difference, but I should have found a significant difference, right? That means that the researcher failed to detect a real treatment effect when there actually was a treatment effect, right? There will be some things that will happen, like maybe the sample size is not large enough, right? Or maybe the difference in the mean and the population mean they're not different. It's not as big as it needs to be, right? But that means that the sample means do not follow this critical region, even though the treatment has an effect on the sample, right? And again, there are several various reasons why we might get a type 2 error. Okay. Type 2 error, again, is the probability of a type 2 error. So beta, okay, the beta, so we did alpha level for type 1 error. Our beta, that's the probability for a type 2 error. And it depends on your sample size, and it depends on your effect size. Your sample size is just how large the sample. So 1 to infinity. And your effect size is really dependent upon the difference between your sample mean and your population, right? So your effect size is the size of that effect, the size of that difference. Okay, what is the size of that difference? Okay. All right. The type 2 error, again, you're failing to reject the null hypothesis when the null hypothesis is actually false. That means I'm saying that there's no difference with my data, but there actually is a difference. There actually is a difference. There actually is some significant difference there. Okay. And just know that beta is that probability. of getting a type 2 error. Go ahead. Yeah, the weird beat. Beta. You better learn these now. Get it? You better learn. You better learn. Uh-oh. Crossing the burning sand. All right. Man, it's kind of indescribable. Something that you say when you cross something like that, it's in you already, but it just solidifies it. Oh man, that movie was sad. That movie was sad. Yeah. All right. All right. So here is a decision graphic chart. Okay. So when we start so, and this is the action question we have. So if the researcher rejects the null hypothesis, when you reject the null hypothesis, what you're saying is that the sample mean, the population mean are significantly different. You're saying when there is no effect whatsoever, no hypothesis is true, that's when you live in the time. That's when you say that there is a difference. It's type 1. Okay? When you make a decision, you filter it. You say that there's no difference, there's no treatment effect whatsoever. And there actually is an effect, there actually is a difference. That's when you make type 2. That's the baby. Just do it first. We talk about size, we talk about the effect size. Those are two of the characteristics of type 2 that is associated with the reason why you might detect the type 2 person. When you reject when there isn't one exists, not exists. There's no difference. There's on the outside. Okay. Questions about type 1 error, type 2 error. They get kind of just know. Yeah, just know. Type 2 error, type 1 error is when you reject the null hypothesis, and the null hypothesis is true. Type 2 error is when you fail to reject the null hypothesis. Okay? Fail to reject it. That means you say there's no difference, but there actually is a difference. Okay? All right. So here are our boundaries for our critical regions that I mentioned here. Okay. Those are our boundaries. All right, true, false. It says a type 1 error is like convicting an innocent person in a jury trial. Think about the anecdote we used, I think it was last week. Think about it. You said what now? So with a jury trial, we're trying to gather enough evidence to no, we're trying to convict a guilty person. That's what we want to do, right? Okay. So in our case, for a jury trial, when you reject the no hypothesis says that he didn't do anything. That's the no. Absolutely. Right? So when you reject the no hypothesis, that means that he did something. When I fail to reject, that means I think he's innocent. So the type 1 error says what? Okay. Yeah, it says we're Think about it. It says you're rejecting a null hypothesis that is true. And the null hypothesis in our case means that he's innocent. It would be true. So, yeah. So when you reject the null hypothesis is he didn't do anything. The alternative hypothesis is, yeah, he's guilty. He did something. So when I reject the null hypothesis, that means I think he did something. But for a type 1 error, it's like you convicting an innocent person, right? Yes. Yes. Good. So it says type 2 error is like convicting a guilty person in a jury trial. Good. Right. Yeah. Yeah. So convicting a guilty person is not an error, but acquitting a guilty person would be like a type 2 error. So you said acquitting a guilty person. So that means I said that I failed to reject a null hypothesis. And the null hypothesis was no, I'm failing to reject when I should have rejected. That means I'm acquitting him, but he's actually guilty. Yeah, something like that. Or it's like OJ, OJ Simpson. He killed her. I know he did, but they acquitted him. That's type 2 error. Yeah, but we knew. I don't know. We know he did, but I mean, all the evidence showed that he did something. Something happened, right? But again, they acquitted the guilty person, so now he can't go to jail for that. But he's still having life. Yeah. Okay. It's type 1 error, type 2 error. Okay. Be able to know the difference. The guilty, the jury case, that gives you a good kind of an analogy, kind of put two and two together. But you should be good with that. Okay. All right. So again, as a summary, you're just going to state your hypotheses. Okay. Select your alpha level. Once you select your alpha level in step 1, then you're going to locate your critical region. So again, you select your alpha level, which is 5%, 1%, 0.01%. Then you're going to set your criteria for your critical region based on your alpha level. Once you've done that, you're going to compute your test statistic. That's going to be our z-score, because we're going to go through an example here shortly. And then you're going to make a probability-based decision off the null hypothesis. So you're either going to reject the null hypothesis if your z-score falls into the critical region, or you're going to fail to reject the null hypothesis if it does not fall into this critical region, if it falls anywhere in here. Okay. It's going to make a lot more sense once we begin to look up problems. Okay. Hey, let's say your mom in school. Here's a summary. Just a summary. Right. Do this. All right. So when you see, and many of you have selected articles where you're going to see results where it says something is significant or statistically significant. Okay. So when it says that something is statistically significant, all it's saying is that the results that I got are very, very unlikely to occur when the null hypothesis is true. And when that is the case, you're going to reject the null hypothesis. Okay. So when you see that, they say the differences were significant, so statistically significant, that means that there is a difference between the different scores, whatever it is, okay, based on a probability that they form using an alpha. They always use an alpha. Okay. So when you see it in the APA format, they're going to report that you found a significant effect, or they'll say it's non-significant, right? They'll say it's either significant or non-significant. They'll report the value of whatever the statistic is. So it can be Z-score, T-score, we'll see F-score, you'll see correlation, and they're going to report their p-value or their probability. Okay? And basically something very similar to this. So it'll say, Rambo ratio had a significant effect on the size of the tips left by metal customer. This is my Z-score of 2.40. When you see 2.40, that's my Z-score. Right? They compare that 2.40 to my critical region. Right? 2.40 falls out here. So that means you reject enough points. And this is P value less than 0.05. So they did this study on tipping behavior on males, and they gave this one young lady, I think it was two separate occasions. They had her wear a blue shirt on one day, and then they had her wear a red shirt on the other day. Same lady. And they were looking to see the amount of tips that male customers left her based on the color of the shirt. So what they found was on the red day versus the blue day, there was a significant difference between the tips that she got on the red day, significantly greater than the tips she got on when she wore the blue shirt. Yeah, it's like. Mm-hmm. You got a blue dress. Yeah. No, it's good. It's good. Okay. So again, you may see something like this, very similar in your research paper. Okay. You very well may see that. Okay. All right. Sure. So what we're going to do is we're going to learn how to again, calculate our Z-score, and we're going to learn how to compare that Z-score. Not really learning, but we're going to do that so that you can make your decision. And that's how you do it. Maybe ask for something like in in the future. Yeah, in the future. Yeah, yeah, yeah. All right. So here are assumptions. When you think about statistics that we're going to be running next week, there are several assumptions that we're going to make. But these are going to be factors that influence a hypothesis. Okay. So the first assumption to the factor that is going to influence is going to be the size difference between the sample mean and the original. That's one of the first factors. So the larger your discrepancy, or the larger the difference between the sample mean and your respective population mean, the larger the z-score. Right? Because if you think about the z-score, so the larger this discrepancy, the larger this is right? The first one. The second factor says the variability of the scores. So it says the variability of the scores, the more variability you have, the larger your standard error, meaning the larger your standard error, the smaller your z-score. Right? You want a small standard error to increase your z-score. The last thing is the number of scores in your sample, so your sample size. The larger your sample size, the smaller your standard error. Okay? So you want a large sample size and you want a large discrepancy. If you have both of those at the same time, you're going to have a large z-score. If you have a large Z-score, then the likelihood that you're going to reject the general hypothesis is going to be very, very high. Very, very high. You at least want your Z-score to be greater than any of these scores. Yeah, it's 5%, 1.96, 0.58, 3.0. Those are the set numbers. Those are scores for those values. That's for a Z. That's for a Z or a normal distribution. All right. But again, you want a large difference. You want and a smaller variability. Just small gives you a smaller standard error. Discrepancies. Yeah, it could be a discrepancy. Yeah, it could be. You have larger discrepancies and larger differences. You ever seen a discrepancy on your receipt? Oh, mm-mm. You ever got your receipt back and you was looking at what you ordered and it ain't look right? Oh, yeah, I need ordered this margarita. Oh my. Hold on, what? $800? You didn't do it on her? They just be doing. How many times have they done it? $800 though? Gee, that's tough. Not excuse you, but how across that screen. And them still didn't get in a fight with a gas station attendant in jail. They can call your name on it. They gonna have to say and them too. They can't say they go put and them too. What you mean? They go, yes. Yeah. Smiles, mug shots. Y'all know y'all ever seen Love and Marriage Husband? Y'all know Destiny? She used to be on that. That most of them cheated on them. You talking Marcel? Oh. Oh. And then his kids played track. And it's not school. You know what I'm saying? That's you got the rest of the song. I think she was 40 checks. It was never that way. It was like I was wondering, this is like stuff people like trying to make and trying to go. Right. When you think about the hypothesis test, especially using Z-scores, there are several assumptions. We're going to talk about assumptions the rest of the time. I have to have these assumptions in order to run these statistics. Right? One of the first assumptions that assume is happening in hypothesis testing is that the samples that we're getting are random. That is one of the major assumptions that we make. Okay? The second assumption that we make is that every observation, every data point that we get is independent of one another. Okay? That means that one data point is not dependent on another data point. Right? It means that they are each individual data points. Right? They're not related in any way. They are completely different. Okay? So if Juanisha scored 85 on the test, her test score should be dependent on Layla's test if they cheat. All right. But again, they should be independent. Everybody's test score should be independent observations, unless y'all work together. That would be dependent, because now y'all work together. Your score is dependent on how they do. Okay. The second thing is the value of the standard deviation. is unchanged by the treatment. Okay? Meaning there should be no change in the variability based on the treatment or the treatment effect. Okay. And then the last one is quality of soil coming from a normal sampling distribution. Right. So that's the reason we're able to use that unit on the table. Because our sampling or our samples are coming from that normal sampling distribution. Okay. When you get four different assumptions, these four different assumptions must be met before we can run a hypothesis test, especially with these. Right. When we move on to the t-test, which will be probably come back. Right? But again, independent observation, those are going to be things that we are going to have to again, equate for assumptions for other tests. All right. Okay. As a check, and then we're going to do some examples. Okay. So it says a researcher uses a hypothesis test to evaluate the null hypothesis, which is the mean is equal to 80. Okay. Which combination of factors is most likely to result in rejecting the null hypothesis? Think about those two factors that influence the hypothesis test. You just wrote them down in a couple spots. Which kind of combination of factors is most likely to result in rejecting the null hypothesis? Okay. You just guess. Yep. You look at your note. Huh? You said which one? Go ahead. If it's not A, it's D. You said you choose B. Which you choose? Okay. You chose the guesstimation of C. Loretta, what you choose? What's your guess? You ain't got no guess? Give me a guess, huh? What you guess? Okay. All right, good guess. All right. Actual answer is B. Where do you? Okay, then. If you go back, let's go back here. So these are influences. This means that we go back and stay back here. So it's asking you're rejecting the null hypothesis, right? So in order to reject the whole null hypothesis, you want your z-score to be very large. Okay. So in order to get a very, very large z-score, you're going to have to reduce the variability. So using your variability here, but you need a large n. So the large n is 50, right? They have a small standard error which is 5. If you compare those two, so they have 25 up there, they have 10. The larger standard error, excuse me, the smaller standard error, the larger sample size gives you the biggest z-score. Okay, the biggest z-score. So if I did it this way, show you. So if I were to, let me just say this is uh, 8 or 7. That's going to be 5. Let's do the next one. So he 5, 50 with 50.
Seven.
7 point. What is 7.7?
So we can have this.
Divided by 7.07. So, yep. 0.707. Yeah, actually, we'll do 7. Good. All right. So now we're going to get our Z score. So for A, Z score is 85 minus 80 over 20. That's 5, right? Okay. For P, 85, 80, 7.04. Okay. Right. So in this instance, I'm probably going to reject the null hypothesis anyway because they're greater than these, right? But this is more extreme.
So when you mean greater than 0.04,
Yeah, it's out here, the critical region. Yep. Yep. Yeah, we're just looking at the way it influences the Z score. Yep. But they would both be, I mean, they were both rejected, but this one was rejected by way more. Okay. Just by using or by changing the sample size and your variability. True or false? It says in effect, existence is more likely to be detected if the N is large. The second one says an effect that exists is less likely to be detected if the standard deviation is large. So if I increase my, let's do this one. So let's do this. So now let's do this. Yeah, we're gonna call it 10. 10 over square root of
it's, wow,
2. Right?
wait, wait.
Okay. So then I put that up here. So then you got C 85 minus 80 over 2. Say 5 over 2, 2.5. See how I reduced my Z score? Right? So as you increase your standard deviation for this value, you decrease the likelihood of chance. Okay. So if I were to increase it to 15, this would have been underneath that 1. Right? So we failed to reject the hypothesis.
So increase. Well, or like,
This is an effect that exists is less likely to be detected if the standard deviation is large. That's true. Because if it's large, then it's not going to be able to detect.
Oh, the change.
Yeah. It being in this critical region is telling me that there is an effect. There is a significant issue. Yeah. There you go. All right. Let me do some examples real quick. I need to. I'll come back to that. Mm-hmm. I'm gonna come back to that. Do this. Let's do an example. We'll come back to the tail tests. And I'm not going to do, yeah, let's do this. Yeah, all right, let's do this. Mm, all right, let's do this. Okay. Here's my point. It says, see, I'm expecting this for here's the group self-esteem lessons. It says in a representative study, a sample of 100 lessons in 100 with a history of group participation is given a standardized self-esteem questionnaire. For the general population of adolescents, scores on this questionnaire form a normal distribution with a population mean. This is my sample. It says the population mean is 50, and the sample or the population standard deviation is what? No. Yeah, I'm just going on an example. Okay. So then it says the sample of the group participation adolescents at 100 has a mean of 53.8. Go ahead. Go ahead. You. This is the This is the population mean. Yep. This is for the population. This is the pop for the sample. Yep. Then you got the sample size. Okay, it's 100. Okay. Given this information, and we're going to do this. Okay. So we're going to use what we call a two-tailed test. And we're going to use a 5% significance level. So our alpha level is going to be 5% or 0.05, which is decimal. That means what? What is our Z score? Oh, for our critical region. Good. Right? So our Z critical, Z critical plus or minus 1.96. Already know that. Know that off top. That's my theory. Okay. So now what do? We're gonna find our z-score. Our z-score, we have our sample size, we have our mean. Now we gotta find our what? Standard error of the mean. To find your standard error of the mean, again, this is the standard error of the mean formula. Square root of 100. I'm going to n. So that means that I have my standard deviation. I have standard deviation to continue over square root of what? 100. Yep. 15 over 10. Standard error of the mean is 1. Big M, sample mean minus my population mean over my standard error. Okay. So then what do? See if I got all this. So now just plug in. All right, I have my mean minus 50.5. That's my Z. So you got 3.8 over 1.5 gives you 2.53. 2.53. So, all right. So my step one is here. This is step one. So, and I'm gonna show you. Actually, not step one. This is step. This part of step one. That's what step one is. Say my hypothesis. Hypothesis. No hypothesis. No hypothesis. Step what? If there is no change. So what you would do is you would just say, good. So we have it would say it says this. Does this sample provide enough evidence to conclude that self-esteem scores for these adolescents are significantly different from those of the general population? So I'm looking to see if there are. So the population, excuse me, or the hypothesis would say that my sample is going to be equal to those people, right? There's no difference. That would be my first hypothesis. Means that there is no difference whatsoever between those two groups. Now, research hypothesis say the alternative is say that the mean is not population. Okay. Everybody see that? Mm-hmm. Okay. It's not equal to, meaning that there is difference. All right. So that's the first step. This is the second step. Setting a curve region. Okay. This is your third step. So getting your standard error of the mean and your z-score, that's your second step. Your third step, excuse me. And then your fourth step will be what? You're making your decision. So given that I know that my z-score is 2.53, then what decision am I going to make? What am I comparing to? So if you remember, this is my graphic distribution. My mean is population, 0 is 50. Okay, so I know that it's going to be plus 1.96 minus 1.96. Okay, these are my z-scores, my critical region. I have a z-score of 2.53. So where does that z-score fall? Falls outside of here, meaning what? Well, it's inside the critical region.
Oh, like, maybe,
2.53.
oh, it's not, it didn't go. Yeah, right.
So we said our critical region is 5%. 5% is 1.96. It's 1.96. 1.96. Yeah, and these are rejected hypothesis, and I because this value falls in the critical region, you're rejecting all. No hypothesis.
So it's still. Good being forward.
3.20 is 0.01%. We set our alpha level at 5%. So we set it at 5%. We didn't set it at 0.01%. It's in the critical. What's your question? We set our critical region at 5%. Okay? So this is outside of it. This would be in the region because it's in the orange. Okay. Outside would be less than 1.96 or less than -1. Then you would have failed to reject it. But since it fell in the region, that means it's in this region. That means you reject it. Yeah. But at the beginning, they give us what our critical region is going to be. So we can set it. You can either set it at 1%, do that 2.58, or it can be, so yeah, we did set it at 1%. And we got this. And we will fail to reject because it's outside of it. Yeah. Yeah. I think so we about that. I will show you this though. Actually, I will show you this one cell test. Okay. One cell test. So say that for this hypothesis, they said that if young people, again, played recreational sports, that their self-esteem score greater than those of the original population. Right? If they said gave the direction, that means that your hypothesis would change. So I'm going to change the hypothesis slightly. So in the direction, they're going to say that my goal hypothesis. If I said that my mean, my sample mean is going to be greater than, then it would say mean is less than or equal to the population. Okay, that would be the no hypothesis. Less than or equal to. If I wanted my research hypothesis, it would say, it's greater than. Okay? That's where my hypothesis. That's the direction. That means I'm almost certain that those who participate in recreational sports are going to have greater self-esteem scores than those who not. Okay, and I can go ahead and set it. If I did it that way, in my 5% significance level, so I said that one-tail test, a one-tail test would look something like this. We'll get on this. Y'all need it? We'll get on it. We'll do an example like this. Okay. So for a one-tail test, and I want it to be greater than, I still have the same mean, okay? But my one-tail test would be on just one side, right? And so this would be the one side, okay? And this would be 1.65. Okay? Just one side. And this is Z-score for a 5% significance level. One side.
That's one.
One-tail
So
test.
how would you do that another thing for that first thing?
Research, they'll say, I believe that instead of it being two-tailed, I believe that there'll be a greater self-esteem score. And if it's greater than, it's going to be a one-tailed test on the right. They say less than, except for that. Yeah, one-tailed test. So that's the greater than and the greater than equal to, that's one-tailed. Right? The equal than or not equal than, that's two-tailed. Questions? Any questions? I think that was all I had. Go ahead. So you can write it like this. Right?
But it's still in the shade, they go over each part
Mhm.
for 5 3.
So say that part again.
I'm sorry, this for, I was looking at it right, because it did 2.53, even though our state number is 5.6, still can go over 0.01, 3.3 here. I know, so I'm just saying it's in the region, they go over this.
I was in the region because it's when I said that critical point at 1.96, 5%, that is what I use. That's what I use. I don't use any of the others.
Mhm.
Once I set it at 5%, I'm not using 1% or 0.01%. So you don't have to worry about this. All I'm worried about is this.
Okay. I don't know.
So it's 2.53. It's greater than 1. The region, if it's in that region, you reject my thoughts. If in this open middle space right here, you fail to reject the no thoughts. Because it's not in the group. You just gotta get the semantic down. Go ahead. So you all are using the 1%, the 0.01%. Once I said it, once I said it at 5%, I'm not using 1% or 0.01%. Throw that out. That's it. That's it. Doesn't matter. You're only
Yeah, so if it's 5%, then as long as it's not in here, then they're check. And that.
side. Well, these people, no, that's it. 2.58. Then 1%. Then I'm not taking into 35%. I'm just looking at 1%. And if I was doing that, then I know that this 2.53 would not fall into that group. Right? It would fall into the white region, which would mean you failed to reject. It's always using 1%. But we're using 5%. We're using 5%.
Yeah. I'm gonna do it.
Right. Two. All right. Thank y'all for being here. If you want some, hey, bye. Please. Trying to get rid of them. Trying to get rid of them. Say it. Yeah. I'm gonna get rid of that is. This is one tail tip. I'll explain this a little bit more. So that's when it's direction. So right now, this is non-directional, meaning it has two tails. Okay. This means that it is directional. And so you're gonna have one tail. So it's gonna look like this. If it's two tailed with equal signs and not equal signs, and when it's two tailed, you have direction sign. Greater than, less than. Okay. But yeah, we don't have to worry about that now. Wednesday. Yeah, Wednesday we'll talk. All right. I think that was it. Yep. That is it. Okay. Anything? Yeah. Oh, two tail, one tail. In this slide deck. Oh, this one. Yeah. So for this one, what I did was up here we calculated our standard error first. I wanted you to see that using standard deviation of 5 and then changing the sample size of 25 to 50, how that changed the result. Okay? And I can actually change the size of the z-score, right? So when we did 5 and 25, it was like 5, 5. We did 5, 50, z-score. So change, decrease. That's you increase your z-score, you increase the likelihood that you point. So that's what. So the larger your z-score, the larger likelihood it's going to fall somewhere into these regions. So that's it. But if you have any questions, I'm available. Have a good one.